So let me try to work one more of these kind of, symbolic simplification problems like we did last time. So see if I can find a good one in here. I'll try to work an even problem because, you got answers to the odd ones, right? By the way, I think we should have a quiz Monday. Because I owe you. The more quizzes we have, the better you guys are going to do on test 2. That's just the name of the game. So it's in your interest for me to give you quizzes. It will help you actually. Let us try out number 14. Well, should I pick the meanest, baddest character on the block here? I should. All right. See what you've done to me. Number 14 then. It looks horrible. Here we go. We are supposed to simplify tangent x over cosecant squared x, all right, plus tangent x over secant squared x, all right, times 1 plus tangent x divided by 1 plus cotangent x, all right, minus 1 over cosine squared x. All right. Let me take a step back to look at it here. That is just unpleasant. Number 14 from section 7.2. I don't think I assigned this one, but probably good for us to work through it. I may regret that statement. So I can't just add these fractions, right? Because they got different denominators. That's annoying, right? And nothing's really popping out at me. So you know what I'm going to do? I'm going to convert everything to sine and cosine and see where that takes me, all right? So what is tangent? Sine x over cosine x, right? So we have that upstairs, and we're dividing by cosecant squared. Well, that's 1 over sine x, sine squared x, yeah? So that's that. And then we've got a sine x over cosine x, that's the tangent, divided by 1 over cosine squared x. So that's all this. Then we've got 1 plus sine x over cosine x divided by 1 plus cosine x over sine x. And all of that minus 1 over cosine squared x, right? All right. So a wise course of action, I think, would be to simplify these fractions before we try anything else, right? So you guys know how to simplify. You know how fractions simplify, right? If I've got a over b all over c over d, how does that simplify? That simplifies to ad over bc, right? That's how we simplify compound fractions. So when I'm looking at sine x over cosine x over sine squared, that actually gives me a sine cubed x over cosine x, right? And the next one, it gives me sine x cosine squared x over cosine x. Aha! Aha! Now I see something. Now over here, That expression does not give me joy. I suggest we multiply this fraction by I'm going to multiply that by, I think if I multiply that by sine cosine over sine cosine, good things will happen to us. That's my intuition there. So what I'm saying is we can multiply by 1, right? So the one I'm going to multiply this by, I'm going to multiply that by sine x cosine x over sine x cosine x. If I do that, that will clear out both of the denominators in the fraction, right? So multiply by that, and we'll get sine x cosine x. What happens when you multiply sine x cosine x times this? You get what? The cosines cancel, and you get sine squared x. And then divided by sine x cosine x plus cosine squared x, right? And all of that minus what? 1 over cosine squared. Whew, goodness. Now, the reason I was giddy about this one here is I see a sine squared plus cosine squared there. See, I can factor out, see what I can do? I can rewrite this as sine of x times sine squared x plus cosine squared x divided by common denominator of cosine x, right? So that's a nice simplification, right? Can you see anything we can factor out of the other two? Like these ones up here, I can factor sine x out there as well. I got like sine x cosine of x plus sine x, yeah? And downstairs I've got cosine x times sine x. Oh, look at that. Look at that happy accident. See that? See that? See that? So look at this. This simplifies to 1. And there's a common cosine plus sine in the other factor. So we can cancel that out. Right? So what do we got? We've got sine x over cosine x times sine x over cosine x minus 1 over cosine squared. Aha, but cosine times cosine is cosine squared. So we actually have a common, shared common denominator in both these terms. So we can rewrite this as sine squared x minus 1 over cosine squared x. What is sine squared x minus 1? Cosine squared x, yeah. So, what we got? We've got 1. This expression simplifies to 1. Wow. Wow. That is what we call algebra, right? Now, if I was to put this on the test, this would be a bonus question, right?
Just wrote 1. Would you do that?
I would be impressed that you somehow saw that. I mean, if this was a problem on the test and you wrote the answer, first of all, this won't be a problem on the test because we did it literally in class. So well, I don't know. Anyway, But no, if you just wrote 1 and that was correct, I mean, I'd have to give you credit. But I would also be like, how did you do? Well, no, I mean, you get more credit if you showed the work, of course, but I would give significant credit for getting the right answer here because it's just good grief. How? All right, so enough of that. I hope I've shown you. I mean, you guys got to chew on some of these for yourself, right? Like work about 5 problems in this section. You know, more you know. I want to talk a little bit more about standard angle, all right? So I want to talk about a little bit more about the logic of how we find standard angle, right? So let's look at a few different cases. So let's find the standard angle of the point 1, 1. Let's find the standard angle of the point, let's see here, 0, 1. Let's find the standard angle of the point -1, 1. And let's find the standard angle of the point -1, -1. Let me make a little bit more diversity here. How about this one? I'll make it, I don't know, -2, comma, -1. Let's find the standard angle of 0, -2. Find the standard angle of, let's say, 2, comma, 1. All right, let me give these names. A, B, C, D, E, F. All right? I want to talk to you about the use of inverse tangent, the use of the inverse trig functions for ascertaining the angle. All right? I want to talk about the success and failure. I want to talk about, does it work? Does it not work? Right? You be the judge. So we have the relation, right? That the tangent theta is y over x. This is true for x not equal to 0, right? So tangent theta is y over x. This is true for most of the plane, right? Most of quadrants 1, 2, 3, and 4. The place it's not true, the y-axis, right? The y-axis tangent theta is not defined, right? Because the y-axis is where x is equal to 0. Okay, so if this is true, this would tempt you to think that theta is inverse tangent of y over x, wouldn't it? But I would caution you, conditions apply. Let's try to understand those conditions, all right? So as a starting point, we're just going to try to calculate the inverse tangent of the point. So inverse tangent of 1 over 1 for A, right? That's inverse tangent of 1. What's inverse tangent of 1? Inverse tangent of 1, pi over 4. It's pi over 4. You can check it out in your calculator if you like. Is this the standard angle of 1, 1? And let me suggest we use the notation. Yes, the angle of 1, 1 is in fact equal to pi over 4. Right? The inverse tangent served us well here. All right? How about the point, how about B? What happens if we try to calculate the inverse tangent of, 1 over 0? What's 1 over 0? Undefined, right? So this, not going to do it, right? So how do we figure out the standard angle of B? What is the standard angle of 0, 1? It is equal to pi over 2 through just basic geometric reasoning, right? Through the unit circle. We know that that's pi over 2. We don't need inverse tangent to figure that out, right? C. Let's calculate. The inverse tangent of y over x is 1 over minus 1, right? So we have inverse tangent of minus 1. What's the inverse tangent of minus 1? Well, inverse tangent's an odd function. That's actually minus inverse tangent of 1. All right? But we know that the inverse tangent of 1 is pi over 4. So we have minus pi over 4. Let's picture that. Let me draw a picture specifically for this case. We've got this point over here, minus 1, 1, right? And we just got inverse tangent to give us what? Minus pi over 4. Where is that? Minus pi over 4 is down here, right? It's down here. That's the wrong angle, right? Inverse tangent has failed us here, right? You can't just take the inverse tangent of y over x to get the standard angle of a point in quadrant 2. It doesn't work, right? Because the inverse tangent, this is always minus pi over 2 less than theta less than pi over 2. Inverse tangent is always going to give you an angle between plus or minus pi over 2. That's its construction, right? So how do we get, okay, great, but it's not that the inverse tangent isn't useful to us here, right? Right? So how do we get the angle in this case? It's equal to the inverse tangent of 1 over minus 1 plus what? Plus pi, right? Plus pi, because we want to go geometrically reflect all the way back around. So that's like pi. I'll draw a picture. So adding pi is like this. And so what we have is minus pi over 4 plus pi, which is 3 pi over 4. Moral of story, if you're in quadrant 2, you have to add pi to the inverse tangent of y over x to get the correct standard angle. All right? How about D? What's going to happen with D? We do inverse tangent, excuse me, minus y over x. That's inverse tangent of a half. What's that? Let me get out my handy dandy calculator here and figure it out. Hopefully this isn't a standard angle. That would be embarrassing, wouldn't it? It might be. I don't know. I haven't thought about it. I just made these points up at the start of class here. So 1/2. Well, anyway, my calculator tells me 0.4636, whatever. Right? Now, if I divide that by pi, I get, okay, so that's about 0.1476 pi, just to give you a sense of it. Pi over 6, so that's kind of close to 30 degrees. It's kind of close to pi over 6, right? So the picture here is what? Our point is over here, right? and our angle is here. So we've got the wrong angle. So what do we do? Subtract pi. You could do that. We could subtract pi. What else could we do? I mean, I think you got choices, actually, right? Now, if we do 0.4636 minus pi, what do we get? I get minus 2.67, roughly speaking, radians, right? On the other hand, if I do 0.4636 plus pi, what do I get? I get 605, yeah, radians. So this is a little bit beyond pi, right? And I don't know, I mean, it's up to you. They're coterminal angles. Subtracting pi or adding pi gives us a pair of coterminal angles. So you have choices. You could subtract pi, or you could add pi to get the standard angle here. But you definitely have to do something, right? So to add pi would be like this. And I mean, I would say do that. That's my personal preference. So the angle of minus 2, 1, minus 2, minus 1 is the inverse tangent of y over x plus pi. That's going to give me an angle that's between like pi and 3 pi over 2. If you want an angle, if you want your standard angles to go between, pi and 3 pi over 2, do that. If you want your standard angles to go between so there's different choices but Jared, I think you're right in terms of in complex analysis, we use what's called the principal argument of a complex number. Subtracting pi would be the correct argument there. If this is what you should do if you want minus pi less than theta, less than pi overall. If you want your angles to land between minus pi and pi, subtracting pi would be the right move there. But listen, I don't really care if you add pi or subtract pi. The point is I want you to understand that you can't just take the inverse tangent of y over x and be right in quadrant 3, right? Yeah. So yeah, I think that's a one fix, or you could subtract pi. I guess you could probably subtract pi in case C too, couldn't you? Because subtracting pi would have been like this, right? So subtracting pi was also an option there. All right, E, where was E? 0 minus 2. Notice this time we're not at pi over 2, we're at what? Inverse tangent's no help to us because 2 over 0 is not, minus 2 over 0 is not defined. And we just need to know our basic trigonometry that that's minus pi over 2, right? Or 3 pi over 2, depending on how you want to look at it, right? And then finally F, we've got 2, 1, right? So inverse tangent of 1 over 2, well, we figured that out before, up here, right? 0.1476, oh, excuse me, 0.4636. And indeed, that makes sense, right? So inverse tangent of y over x worked for us in quadrant 4. Indeed, this is equal to the angle of 2, 1. So to summarize, inverse tangent is going to give you the correct answer in quadrants 1 and 4, and it's going to give you the wrong answer in quadrants 2 and 3. And it's going to give you an insane answer unless you want to take a limiting perspective on the y-axis. All right? Excuse me. But anyway, I thought I owed you guys that. So, let us move along. I have things to show you today. See how far we get. It sounds like a jet, doesn't it? All right, guys, so what is that? It's just a helicopter. Okay. All right. Let me get to it. I've got some things to prove for you today. See if I can get my ducks in a row here. So, start out with a fundamental lemma. Well, theorem, really. If we have a triangle, and we have, let's say, B, A, and theta, all right? The area is 1/2 AB sine of the angle that's between A and B. All right? This is a theorem. Here's the proof. So all you got to do, is, let me try that again. I'll draw it like this to make it easier to see. So if this is B, good grief. No, I'm sorry. Let me draw my picture better. Golly. Who knew helicopter taking off could be distracting? Let's try this again. So if this is B, I can, golly. It's not happy with my stupid triangles. I'll eventually get it right, guys. I just don't. Yeah, that one's good. But the point is, drop a perpendicular from B, right? If we do that, so we know that the area of a triangle is 1/2 base times height, right? But, so here the base is B. And what is that? Well, this is, see that right triangle right there? So that's the opposite. This is the hypotenuse is A, the opposite side, right? So this is A sine theta, right? The height is A sine theta. So we have A sine theta. There you go. So if you want to find the area of a triangle, if you know two sides and the angle between them, you can calculate the area with this formula. Easy as that. All right. So keep that in mind. Now I want to draw a picture for you. All right. And so we'll put point P up here, point Q down here, R over here. I'm going to drop a perpendicular right here. All right. These are both right angles. Call this point in the middle N. All right. And we'll call this R. We'll call this length Q. And we'll call the middle one H. All right. This will be angle A. This will be angle B. All right. So let us start by making the observation that the area of PQR is equal to what? Well, it's equal to the area of the two triangles that are composing that triangle PQR, right? You see that? So area PQR is equal to area QPN plus area PNR. Right? Agree? I hope you agree. However, we can calculate the area of every one of these triangles using the theorem I just proved. Right? So like area PQR, well, that's 1/2 RQ sine of A plus B. Right? On the other hand, the area of QPN is 1/2 RH sine of what? Sine of A. What's the area of PNR? Well, it's 1/2 HQ sine of B. Right? However, notice that H is equal to R cosine A. And H is also equal to Q cosine B. See that? Right? Because H is the adjacent side and R is the hypotenuse. So we do R times cosine of A to get H from the left triangle. And we do Q times the cosine of B to get H from the right triangle. These are both true. So we can substitute those into the equation above, and what does it give us? I'm going to put this one into this one, and I'm going to put this one into that one. All right? So I get 1/2 RQ cos B sine A plus 1/2 RQ cos A sine B. Of course, we can then do what? We can divide the whole equation by 1/2 RQ, and what do we find? We find that the sine of A plus B is equal to, I'll write it this way, sine A cosine B plus sine B. I mean, you can write these in whichever order you want. I'll just write it. Oh, fine, I'll write it the other way. Cosine A, I can't make up my mind. Sine B, it doesn't really matter. You can commute these terms. They're numbers. They commute, right? But there you go. This is the beloved adding angles formula for sine. So what could we do with this formula? Application. Try it out. Let's try it out for size. What happens if we do sine of like theta plus pi over 2? So put A equal to theta, put B equal to pi over 2. We get what? We get sine theta cosine pi over 2 plus cosine theta sine pi over 2. Now, notice that the cosine of pi over 2 is 0. The sine of pi over 2 is 1. Thus, the cosine of theta is equal to the sine of theta plus pi over 2. So in this way, we can rewrite cosine as a sine, right? On the other hand, we can also look at the sine of theta minus pi over 2, right? Theta of minus pi over 2, well, this would be sine theta cosine minus pi over 2, and then plus cosine theta sine of minus pi over 2. What's sine of minus pi over 2? Again, cosine of minus pi over 2 is 0. Sine of minus pi over 2 is minus 1. So we find the identity that the cosine, excuse me, the So we find that cosine theta can also be written as minus the sine of theta minus pi over 2. This is another way to look at cosine in terms of sine, right? My point to you is that the adding angles formula reveals these things efficiently and cleanly. Now, we've seen these things before in our discussion of like coterminal angles, but this gives us like an algebraic sledgehammer to just crush these kind of questions. It's an amazing tool. Excuse me. All right, so let's look at another question. I told you guys before that if we don't have a right triangle, there's a result that's related to the Pythagorean theorem, which is a twist on it. It's called the Law of Cosines. I'll show you how we derive that. It's part of the same song and dance. So I'll draw a picture. And again, I'm going to drop a perpendicular like this. I'll put angle alpha here. I'll put angle beta here. I'll put B here. I'll put A here. And down on the bottom, altogether, this is going to be C. All right? So let me just point out some things to you. So this is what? Well, this is going to be A times the what? A times the sine of alpha. It's the opposite side. Hypotenuse times sine gives us the opposite side, right? That's this right here. This one right here, well, that's B times the sine of beta by essentially the same logic, right? So the first thing you notice is that we have C is equal to what? C is equal to A sine alpha plus B sine beta, right? Because the total length should be this length plus that length, right? Of course, I'm out of camera. Idiot. There we go. Fortunately. All right, so next, what else can you tell me? Well, this right here, right, is the same side shared by both triangles. So from the left triangle, that would be, let's call it H, right? H is, on the one hand, A cosine alpha, right? But on the other hand, it's also equal to B cosine beta, right? So we have this equality as well to work with. So let us consider then C squared. C squared, A sine alpha plus B sine beta squared, right? Square it. What do you get? You get A squared sine squared alpha plus 2AB sine alpha sine beta plus B squared sine squared beta. All right? Now, I'm going to take the A squared, the first and last term, And I'm going to trade my sine squared for 1 minus cosine squared, as is my right. Right? So I can rewrite this as a squared times 1 minus cosine squared alpha plus b squared times 1 minus sine squared beta, right? And then, of course, I still have my 2ab sine alpha sine beta. All right, so plus 2ab sine alpha sine beta. All right, so look at what we got. We got a squared plus b squared, right? Minus what? Minus a cosine alpha times a cosine alpha plus b cosine alpha, excuse me, b, oh, I'm an idiot. That was supposed to be, that's supposed to be cosine squared. Sorry about that. Cosine squared. B cosine beta times b cosine beta. I'm just writing them out. You'll see why in just a second. Right? Now we can trade a cosine alpha for what? This is equal to b cosine beta, right? And we can trade a b cosine beta for what? For a cosine alpha, because h equals h. So those two terms are actually the same term. In fact, we have twice the product of cosine alpha. Have I done something? Something feels off. Ah, curses. I know now what I've done. I've got my papers out. Well, it's not wrong. It's not wrong. Oh, man. Curses. All right, well, anyway, this is going to give me twice, right, minus 2, minus 2ab, parentheses, cosine alpha, cosine beta, minus sine alpha, sine beta. All right? Something I need to do before we go further than this. So how would cosine of a plus b, how could you write that in terms of sine? How can I change cosine to sine? See, that would be sine of a plus b plus pi over 2, right? But then we can look at this and this as the things. So we've got sine a cosine of b plus pi over 2 plus cosine a sine of b plus pi over 2 by the what? By the adding angles formula for sine. But what is cosine of b plus pi over 2? Cosine, curses. I chose poorly, didn't I? Oh, man. I had this all worked out. Okay, so cosine of b plus pi over 2 is minus sine b. And cosine of a, sine of b plus pi over 2, that is what? That's cosine b, right? So my point to you is we get the following. Cosine a, cosine b. Listen, I'll do this one again, like next class, this particular part. I know it's a little bit rushed. But this is the adding angles formula for cosine. Cosine, cosine minus sine, sine. What do we have down here? See what we have here? Cosine, cosine minus sine, sine. So by the adding angles formula for cosine, this is in fact a squared plus b squared minus 2ab cosine of alpha plus beta. And see that, guys, if we have an angle, if we have a triangle like this, if this is angle theta, this is the side opposite c, these are the adjacent sides a and b, the law of cosines is that c squared is a squared plus b squared minus 2ab cosine theta. This is the generalization of the Pythagorean theorem for non-right triangles. What happens with the Pythagorean theorem is that the angle theta, the angle opposite the hypotenuse, is pi over 2. It's 90 degrees. So the cosine term drops out, and we're just left with a squared plus b squared equals to c squared. So anyway, next time I'll show you a law of sines. I shouldn't have. This is all Jared's fault. I blame you, Jared, because you sucked me into that very tempting number 14 at the start of class. Otherwise, I'd have about 5 more minutes. Well, or if I'd been on time. Sorry.